Welcome! Today, we're diving into a really cool puzzle from the world of energy. Seriously, it's a mix of physics, chemistry, and, well, billions of dollars. We're going deep underground to figure out how on earth you measure a liquid that actually changes its size.
It really sounds like a riddle, doesn't it? How do you measure a liquid that shrinks? But this isn't just some brain teaser. It's a fundamental, everyday challenge for reservoir engineers who are trying to figure out just how much oil is sitting right below our feet.
So to get our heads around this, we have to go right to the source. And I mean that literally. We're talking miles underground, into an oil reservoir. And let me tell you, it's a world that is completely alien to anything we experience up here.
Yeah, you really have to forget everything you think you know about oil being just some black liquid. Down there, it's a totally different beast. It's being squeezed by the weight of miles of rock above it, and basically baked by the Earth's core. And under those insane conditions, the lines between what's a liquid and what's a gas, they start to get really, really blurry.
And all this brings us to the core science of the problem, a little something called phase behavior. It's basically the rulebook that explains how stuff changes from, say, a solid to a liquid to a gas.
Phase is just a sciencey word for a state of matter. Solid, liquid, or gas. We see it all the time with water, right? Freeze it, you get ice. Boil it, you get steam. Simple. But for that complex cocktail of hydrocarbons that's sloshing around in a reservoir, it is not nearly that simple.
And check this out. This is what makes it so tricky. If you have a simple fluid, like pure ethane on the left, it's got a nice, clean boiling point. Hit that temperature, and boom, it turns into gas. But reservoir fluid, that's a messy, complicated mix of hundreds of different hydrocarbons. It doesn't have one single boiling point. It's a whole different ballgame.
So instead of a boiling point, engineers talk about a phase envelope. You could think of it like a big fuzzy zone of temperatures and pressures where liquid oil and gas bubbles are all just hanging out together in this delicate balance. The whole thing is saturated, just waiting for a trigger to let all that gas loose.
Okay, so let's actually follow a drop of this fluid on its incredible journey. We're going to go from the high-pressure darkness of the reservoir all the way up to the surface. And folks, this is where the shrinking happens.
Let's trace the path. Deep down in the reservoir, it's just like an unopened can of soda. All that gas is dissolved right into the liquid because of the immense pressure. But as that fluid starts traveling up the well, the pressure drops fast. Then you hit a critical moment called the bubble point. That's when the very first bubble of gas fizzes out of the liquid. By the time it gets all the way to the surface, so much gas has escaped that the liquid oil has literally shrunk. And this is the absolute key. A barrel of oil underground is not the same as a barrel of oil on the surface.
You can see how this creates a huge problem, right? If your product changes size, how do you measure it? How can you sell it? How do you even know how much you have in the first place? Well, this is where some absolutely brilliant engineering math comes to the rescue.
That's the million-dollar question, or more like the billion-dollar question. How do they solve this puzzle? They can't just ignore it. They need a rock-solid way to convert what's happening in the reservoir into what they're going to get at the sales point.
The starting point is a formula a lot of us might remember from high school chemistry class, the ideal gas law. It's a great little equation for describing how perfect or ideal gases behave. The only problem? In the real world, and especially in a hot, high-pressure oil reservoir, there are no perfect gases. So what do engineers do? They add a correction. They introduce one single letter into that classic formula that makes all the difference, Z. This Z factor is the secret ingredient, the key that adjusts the ideal formula for the messy reality of the reservoir. This little z is officially known as the gas compressibility factor, but really, you should just think of it as a reality check. It's a number that tells you exactly how much the real gas down there is deviating from that perfect textbook behavior, which lets engineers make incredibly precise calculations.
Now that Z factor for gas is actually part of a bigger toolkit that engineers use called formation volume factors, or FVFs for short. These are basically correction factors for every fluid down there. There's one for oil, called BO, that perfectly accounts for how much it's going to shrink. There's one for gas, BG, that calculates how much it's going to expand. And yep, there's even one for the water, BW.
This is honestly the perfect way to think about it. These factors are a translation key. They let an engineer look at one barrel of fluid deep in the reservoir and say with confidence, okay, when that thing gets to the surface, it's going to become exactly this much oil I can sell and exactly this much gas I can sell. It's an incredible tool.
Now, I know this might all seem pretty technical, maybe a little
abstract. But the real-world impact of getting this translation right, it's just massive. I mean, we are talking about the very foundation of the global energy economy. At the end of the day, all of this super complex math is designed to do one thing. Take those chaotic, changing volumes from deep underground and convert them into volumes at a single globally agreed upon standard. Every barrel of oil, everywhere in the world, is measured as if it were at 60 degrees Fahrenheit and 14.7 psi, which is just normal atmospheric pressure at sea level. This science is what makes a global market even possible.
So why does all this matter so much? Because these calculations, they determine everything. They tell a company how big their new discovery actually is. They dictate what kind of pipes and pumps and equipment they need to build. They determine whether a multi-billion-dollar project is even going to make money. And crucially, public companies use these numbers to report their reserves to investors and to the stock market. You can imagine that getting it wrong would be, well, catastrophic.
So the next time you see a headline that talks about billions of barrels of oil reserves, you'll be in on the secret. You'll know that those numbers aren't just found, they are calculated with incredible precision. And it's all thanks to this invisible science, the art of measuring a liquid that shrinks. Thanks for tuning in.